This is a video about mathematical logic. Both the predicate calculus and the simpler propositional calculus will be done. We'll do the simpler one today. We won't use truth tables at all. Instead, we shall use truth trees. So here, for example, is a tree, and this tree has leaves, A, B, C, maybe another one, D, and it has these nodes. These nodes may transmit truth down the tree. A, B, C, and D each can be either true or false, and they send their truth or falsity down the tree. The simple rule which tells us what gets transmitted is this. Truth comes out here is transmitted only if everything going in is false. Or in other words, we could think of it as zeros and ones. A 1 comes out if everything in is 0. So we could summarize the rule as not hit, all zeros going in, transmit, 1 comes out. So if some of these are 1s, then 0 will come out, nothing will come out. And we'll often be working backwards from the bottom because we like to think what will happen. What does this tree say about the statements A, B, C, D? When is it giving us truth? When does truth come out the bottom? That's the kind of question we're going to ask. In which case we'll work backwards up the tree. So for instance, if we've got truth coming down a branch here, then we know we've got 0 falsehood going in. If we've got nothing coming down, then this doesn't apply, so that means we must have some truth going in, but we won't know how much. Okay. So let's take a simple tree. Here we go. So let's suppose truth comes out here, the 1. Then, according to this, the falsehood must be coming out. So if falsehood's coming out, there must have been some truth going in. We don't know whether it's coming from this or both. Okay. So it's telling us that A or B is true. So this tree is the tree for the logical statement A or B, which we use this symbol to shorten the or. Now, when I say A or B, I include both A and B. It's not the exclusive or, it's the inclusive or. Okay, let's mess this up a bit and see what happens. So let's put in some other transmitters in here. Bong, bong, bong. Suppose truth comes out of this. So 1 coming out. Then 0 must have gone in. Some truth must have gone in there. Well, there's only one thing going in, so it must have been a 1. 1 going in. Everything must have been false. False coming down. Everything in must have been true. So now, if truth comes out, A and B are true. So this is saying A and B. A and B. So that tree says A and B, this tree says A or B, and I've messed up. That should be that symbol for OR. It's a bit like a union sign in set theory, if you like. And that's a bit like the intersection sign for those of us who've done set theory. Okay, well, we could actually have had an even simpler tree. This one, just simply that. But in that case, not sure you can see that, move it over a bit. If truth comes down here, false comes out. If false goes in, truth goes out. So whatever A is, what comes out is the opposite. So this is saying not A, not A, which we write like that. Now, if we put not A, we'd have A back again, wouldn't we? So if we had A, and not A, then that's just A back again. So we could sort of collapse that and we just get A. So if we go back to the A and B over here, then we see what comes out of this. If it's 1, 1 will come out the bottom because 1, 0, 1. If 0 were to coming out, then 1, 0. So in other words, we could, if you let me draw bushes instead of trees, I could just chop that off. So in other words, we just do that for A and B. Okay, so now we've got our simple trees. Oh, one more. Let's take a look at this one. A, B. Right. Now, I've been talking about when does truth come out. Now let's reverse this and ask when does false come out of this. False out only when. Okay, so let's see. What will it be? So 0 coming out. So 1 must have gone in. So if 1 comes out, not hit transmit, these are zeros. And if 0 came from there, 1 came from there. So A is true and B is false. A true, B false. In other words, this is what we take in the mathematical world as the definition of if A, then B. Or in shorthand, or like this. And we also say A implies B. So, if A were false, then this would be true. A implies B when A is false. You may not like that, but that's the way it is. Okay, so now let's try combining. What about taking A or B, get that the right way up, and C or D? What would that look like? Well, A or B. No, I don't want it. I want it the other way around. I want A and B. I'll let you do that one as an exercise. Or C and D. So A and B is that. A, B. C and D is that. So now I want to take this A and B. Well, I was wrong. Got it wrong again. A or B and C or D. I'm going to let you do the other one. Sorry, that's made a bit of a mess. A or B and C or D. C or D. So that's A or B, that's C or D. And now I want to AND these together, but this is how you AND. So instead of A and B in here, I put A or B, and instead of B, I put C or D. So, here we go. I put that. And now, you see, we can collapse these here. And in fact, we can collapse this bottom bit as well, and we get this rather nice resulting tree, which is simply A, B, C, D. So as an exercise, find the tree for the other way around, A and B, or C and D. Okay, finally, let's have another think here. Let's look at this A implies B. Look at A implies B. A, B. And compare it with A or B. Whoops, I've maybe gone off the screens, beg your pardon. So this is A implies B, and this is A or B. And notice they're very much the same. In fact, if I were to replace that A with not A, I would get exactly this. So A implies B is the same thing as not A or B. Okay. So what else can we do? Well, if we compare A or B with A and B, we could see that we could make this tree into that one if I replaced AB with not A, not B to get those dots there, and then put a not on the bottom. In other words, not A or not B is equal to A and B. Similarly, an exercise for the reader, not A or not and not B is the same as A or B. So we can express A and B in terms of A or B, or we can do it the other way around. So that's an exercise. Next one, I will carry on to predicate logic, where we allow these A, B's and C's to depend on a variable. So we might have a x, some statement about some x, x could be a number, and the statement could be about that number. It might say x squared is 37 or whatever. Okay, bye-bye.